We've got a question here in which we will go through an entire regression analysis. Now, if you haven't watched the straight line regression analysis shebang video, then I would suggest you watch that first because that does go through a few of the concepts and interpretations that this one will skip through. So the context here is that Richard is looking for a car and he sees a list that shows cars, 20 different cars, gives them ratings and also how much they cost. And he's looking for a car that has at least a rating of 7, and we need to find out what Richard should pay. So reading the question, we can work out that rating here is my explanatory variable. And remember, the explanatory variable is the variable that you're going to choose or adjust and then see what happens to the other variable. So therefore, price in this context will be the responsive variable because that's what comes out. We're going to play with the explanatory variable to find out what happens to the response variable. And here you see all the prices and all the data, which is what we're going to work with. So now that we know what our explanatory and response variables are, we're going to put all this data into our calculators. And there we go, and you can see I've got one column S for score and another column of P for price. What I'm going to do now is I'm going to graph it and see what it looks like. So the first thing is I'm going to go to a scatter plot where I have S for score as my X list and P for price as my Y list. And then I hit the graph button and I get a graph that looks like this, and this is clearly non-linear. So that means I've got some work to do and I'm going to have to transform this data. In the meantime, I'm going to take a quick note of what the graph looks like. And so if I draw my axes here, and of course I have rating and price, my graph looked something like that. And I'm going to keep that in mind because that's going to come in handy later on. Now, to confirm that my plot is indeed nonlinear, even though it very much looks like it is, I'm going to make a residual plot to check it out. So list 3, I'm going to call RES for residual, and I'm going to go to Calc, Regression, Linear Regression, pick my X and Y lists. So I have score and price. And then here where it says copy residual, I'm going to copy residuals into my RES column. And the calculator will immediately calculate all the residuals for me. Before I do that, I may as well have a quick look at the data that this is giving me. And this is all about a straight line graph. Now we know that our graph is curved, or we're pretty sure it is, and we're about to check out the residual plot to realize that it is. But for the time being, we still know that my R value and my R squared values are very high. So it's worth keeping note of that now. So ultimately what this tells us is that for R, for my correlation coefficient, it is a score of 93.07 or 0.9307, which tells us that it is a positive and strong relationship. We believe it's nonlinear. This 86.63, that's the bit that tells you that 86.63% of the variation in car price can be explained by the variation in rating. So this is what we have right now as far as the quality of our data, and it's pretty good. Now, when we transform the data, we're going to want to get a better R squared score than 86.63. So we want a higher score. For now though, let's have a look at the residual plot. So I'm going to my calculator settings and my X list will stay the same, but my Y list becomes the residual plot. That's always the case when you have a residual. So your X list, your explanatory variable, never changes when you're looking at a residual plot. It's the Y list that becomes the residual plot. And I set that, and ignore this line, but you can see there's a definite pattern. So I'm going to make note of that as well. So here we have the rating, and here we've got the residual, and, oops, that's meant to be a straight line, by the way, so let's do a little bit better. And you can see it's definitely a smiley face pattern. So it looks something like that. And because there is a pattern, then it means we're going to transform to linearize the data. If this was random, so in green I'm going to draw a random plot. If this was random, that tells us that it's a linear line. Our assumption of linearity is correct if it's random. But because it's got a definite shape, our assumption that we need to transform is correct. And now, once we know we need to transform, we have to come back to the original graph here. And we can see the original graph has a line that looks like it's in the bottom right-hand side of a clock. So it's this quarter of the circle that we're going to go to when we open up the circle of transformations. And our circle of transformations is this business. Now, because my graph looks like this, then I know I need to look in this part of my circle of transformations, and it tells me my possible transformations are log y, 1 over y, or the reciprocal y, and x squared. So keep that in mind. There's a log function. This is called the reciprocal, or there's the squared function. And I need to try each of these transformations to see which one gives me the highest r squared value. So now we're going to try these 3 different transformations to see if it improves our data. So here's all our data, and the first transformation it suggests is the log y transformation. So I'm going to create a new list that I call ly for log y. Down the bottom here, I'm going to make a calculation which does the log of my price, because price was my y coordinate. So I'm going to open up my keyboard and I'm going to make a log base 10 of y. So here we have this log 10. That's the one we'll always use in further maths. So log 10 of p for price. And it'll make a calculation of all of those numbers. So let's have a quick look at what that graph's going to look like. Now remember, we always have graphs that look like this with our responsive variable on our vertical axis and our explanatory variable on our horizontal axis. The responsive variable, the y, has now been transformed to log y, which means now my vertical axis will be log y and my horizontal axis will still be x. Or in terms of these variables, this here will be log of price, and here it's just going to be the rating. Now let's go to our calculator, and we're going to find out the r squared values, because that's what matters. So we go calc, regression, linear regression, and remember my x list is still rating. I can tell that from the graph. My y list is now log y, which remember I called ly, and then I hit OK, and I find out I've got some really high numbers here. So my r value is 0.9857. So that's an extremely strong positive relationship, and my r squared value is 0.971. That'll be a 7 when I round it off, or 97.17%. That's really high. So what I'm going to do is I'm going to copy this down and keep that on my, make note of that and keep that here. Now, my next transformation that I want to check is going to be the 1 over y. So my 1 over y graph, again, it's going to have my response variable, which is normally my y, is changing to 1 over y, or 1 over price. And my explanatory variable doesn't change, so it's still rating. Notice how we only ever change one of our axes. You won't have a case in further maths where you're changing both axes. Now I'm going to go back to the calculator and I'm going to create my next axis, which is 1 over price, or the reciprocal y. So you can see here I've labelled one of my columns RY. And then down in the calculate area, I'm going to put in the calculation. Now remember, the reciprocal is 1 over, and my y was the price, which I called P. And you can see now it populates that column with new values. You'll notice these values don't seem to make a lot of sense because they've got the E and a number and all that sort of stuff. The calculator does that because it's its way of expressing very big or very small numbers in a very small area. That's all. You won't need to worry too much about that. So now I'm going to find my R squared value, because the higher the R squared value, the better the transformation is for the data we have. Remember, my X is still the score or the rating. My Y is now my RY, my reciprocal Y, and I get this data here. It's still really high, but it's not as high as the previous data. So still, I'll copy the R and the R squared, and I'm going to paste that onto my work as well. And finally, I'm going to look at the x squared transformation, and I'll follow essentially the same process. Remember, when I look at x squared now, it's the explanatory variable axis that changes. So there's y on the vertical, but as x squared, that's now the explanatory axis that changes. So therefore, it's going to be rating squared, which means when I go to the calculator, I first of all make a column which will be x squared. You can see here I've got one waiting, xs for x squared. And down the bottom, I'm going to put the calculation of s squared. And you can see now I keep using s when I should have car rating R, and you can see that I have to remember it. So labeling your columns well can be quite helpful. When I press go, I get a new column. And then again, I'm going to find my R squared value. So my X column is now XS, and my Y column is P for price, and I hit OK. And again, I have some very high R and R squared values. So I'll copy them down, and then I'll be able to compare them. So for my 3 sets of data, I've got 3 lots of R squared values. And the one I'm looking for is the highest one. So here I have an R squared of 0.9565, which is 95.6, actually 6% when I round that off because that's a 5, so this 5 will jump up. My green, my 1 over y reciprocal transformation, R squared is 93.18%. And if I have a look in the orange, my log y transformation, the R squared is 97.17%. And that means we're going to do our calculation based on the log y transformation because the R squared value is the highest. So now we've chosen the log y transformation. We need to get the data about that log y transformation. So I'm going to use the calc again, regression, linear regression. Remember what we did before to get our log y data, which is here. And I'm going to write down the A and B values. So A is 3.49 and B is 0.12. So I'll get that down for y equals a plus bx. A equals 3.49 and b I think was 0.12. So I've got those down now. Now I need to remember that always my equation is written as the response variable equals A plus B times the explanatory variable. That's what this is. But here my response variable has changed to log y. So I'm going to write log of y equals, I've still got the A, 3.49 plus B, 0.12. And my explanatory variable, I've changed the y, my explanatory variable remains the explanatory variable, which is rating. So now I have this as my expression for how I will do my calculation. Finally, we know that Richard wanted a car that had a rating of at least 7. So my equation, log of price equals 3.49 times 0.12, so that should be a plus, 0.12 times my rating, and from the information in the question, that's a 7. I'm going to enter this exactly like this. I'll use a y, exactly like this into my calculator. So here we have the main part, and I'm going to go log of y equals 3.49 plus 0.12 times 7. Now, I really encourage you to use your entire equation and then solve rather than do it any other way, only because less can go wrong. So now I'll highlight that interactive equation, solve for y, and I get an answer of 21,379, and in the context of this question, that'll be dollars. So, therefore, price equals, it was $21,379.62. So this is the expected value of a car that has a rating of 7, according to our transformation. The last thing we want to do is now check to make sure these numbers seem okay. So when I have a look in here, a rating of 7, which, goodness gracious, doesn't appear, is probably going to be somewhere between the 6s, which is 13, 16,000 and something like that, and the 8s, which is in the high 20s or low 30s. So something in the low 20,000s probably suits this data when I compare it there, in which case I can walk away from this question feeling pretty good about my answer.